And we'll start the record here. So we interest, sorry, is someone asking a question? Is that a question or can I continue?
Continue.
I noticed that we've got a shared microphone. Sorry, it's what is it? Okay, so I'll continue from here. Right, so we are interested in K-means algorithm, not to be confused with the lazy learning, which is KNN. KNN is dealing with neighbors. K-mean slightly different. We'll look at it in a second anyway, just because again, they fall under different types of machine learning algorithms, of course, even under the common types that we have. So it's one of the most popular unsupervised machine learning algorithms, K-means algorithm, that's what it is. It's a clustering algorithms, it's a clustering algorithm, and is often used for things like market segmentation, like social network analysis, things around searching for results in groupings or medical imagery, or looking for anomalies, things like network anomalies and other things, right? So in the next couple of slides, hopefully if time permits, we would definitely touch on K-means, but before we do that, we'll be talking more about clustering to look at the various clustering algorithms that clustering techniques that we have. Then eventually we'll look at types, then we'll look at the K-means as an example of it. So understanding clustering, you've got think about things like segmentation, grouping like for like, segregation, finding the odd one out or the elephant in the room in order to put it in the right place that it should be. So basically grouping like for like, right? So if you think about it, clustering is basically an approach, say in machine learning, that is used to categorize or basically to segment the data into subgroups. And if you have, let's say, one subgroup, and I think earlier we used colors, so let's go for that. And hopefully yellow will be clear this time. Oh, yes, that's clear. Another subgroup, and you can have another subgroup as well. That is a bad idea in terms of categories. So let me choose that. So you have different subgroups that you are using, right? And because that looks like a scary face, I'm just going to move on to the next slide so we can work with other slides. So we have step up from machine learning, classical or common methods, straight down to supervised, regression, classification. We've understood that we don't want to confuse the name of logistic regression to think it should belong to regression. It's actually a binary classification. So it falls under classification, and we've got some things that belongs to binary. And of course, we've got some things that belongs to multi-class, and then we have one naive, which falls probation of naive base, and it's frozen 2 seconds and it's back, which can be either or in terms of binary or not. Then we take, sorry, screen frozen, back up now. Then we can have one that we're interested in now. Instead of branching to supervised, we want to branch towards unsupervised. 2 seconds and we back up. Unsupervised, go to clustering. In there, we want to have a look at an example, which is the K-means. So basically, K-means is an unsupervised machine learning algorithm, right? And of course, unsupervised means we are using unlabeled data. So with clustering, we actually have two main goals. We have two main goals with clustering, right? One of the goals is to find things that are similar to each other as possible. Find the items that are similar to each other as possible and put them in one cluster. Then the ones that are dissimilar to each other in terms of between clusters, we want between each cluster should be as different from the other as possible. So within cluster similarity, of course, high interclass similarity. And then between the classes, we want low interclass similarity. That's just our goal. That's the two goals that we have. You happy for me to continue? Okay, up to this point.
Yes.
Okay, so simply we just want to look at some examples of real-world classroom or real-world cases that you may want to apply classroom-based machine learning algorithms. So if you're saying yes, they are widely used, but in areas like networking to detect anomalous behavior, or for security in networking or network security analysis, things like maybe if you want to detect DDoS attack and all those kind of common or well-known attacks and network system. Or things like filing systems. So if you want to categorize documents based on their similarities or the old filing system, you can basically use cluster-based algorithms. Or things like if you want to do something like market segmentation, where you know your customers, look at their buying behavior and say, yes, maybe I want to target these customers more with this new product line that is coming because they are more likely to buy around this time. Or say, I'm going to buy a particular TV time slots, which has advertisements around 9 a.m. every day, because that is where people who buy from me the most watch TV or something, mostly just aligning your product to your customers' behavior, something like that. So let's look at a simple example. Let's say we work for a credit union, bank, or anything, and we say we want to do some small, simple market segmentation, right? And we say we want to group our customers, or we want to cluster our customers based on their spending behavior. So we look at how much they spend and how much they earn. Sorry if I was talking too fast earlier. I'll try intentionally slow down now. So we want to group them based on their spending and their income. And of course, there are other things that you can look at before anyone asks me that. The other things you can look at. We're just interested in these two just to make life simple for us, right? Which means we can take this and then we can draw it into the two-dimensional plane. So we just highlight them out and then we can draw it into the two-dimensional plane and place the customers on there. You can look at the data into a bit detail later. So we've got someone like Sarah, who sort of learned, let me put this is low. And the bottom there, and the x-axis is the income. So we've got Sarah, who is moderately low income earning person, but also spends less, so doesn't really spend much. We've got someone like Frank, who is a low income earner, but spends quite a lot. We have someone like Alan, who earns quite a lot and also spends a lot as well. So we've got a distribution on there, and straight away we can actually see some similarities. So we say, we kind of group in like for like. So we can start off by saying these people kind of look like they all have low income and they spend less. And we can also say another set, the low income, high spending people. And also we can have another group. So based on the way that our clusters have been formed, we can decide whether we are targeting these people or the others, or depending on how we want to use the data. That, of course, hopefully we have the right to use it in ethically. So in this particular case, we say it's called k-means. Sorry, question, please ask.
No question.
Okay, sorry. So when we did the KNN, we said.
Michael, please, I have a question.
There is a question. I thought there was no question. Please ask.
Yeah, please, under the spending column from the table, I want to know what the unit was, because I just saw 7 and I don't know if like it's an amount of money or something.
Let me stop. I don't want to stop the recording. No, I don't want to stop the recording. So let's say you can make it, I don't know, 7 million per year, £7 per year, 7,000 per year. I think it's just a fictitious data set that we are using as an indicator to help us understand how the k-means work. Does that-
Okay, and yeah, and in this case, we are not going to use gender to
No.
for
So yes, there we are. So in this particular case, we just saying, it's just an example. We are interested in, so we say we don't really care. We're not targeting the age. We're not targeting the gender. We're not targeting the education. We are only, our strategy, we are only interested in how much they earn, how much they spend. You can put million on there, you can put 1,000 per year or something. It doesn't really matter. It's just a fictitious data. Does that make sense? Data set, does that make sense?
yeah, thank you.
So it depends on the company's strategy, really. So in this particular point, at this particular point in time, you're interested in these two. Oops, I recorded over that recording. Hopefully it just continued. Otherwise, I'll use a different recording or just re-record this for you again. So I'll continue. Sorry, are there any further questions for me, or can I continue? Does that continue? Yeah, okay. Hopefully you can hear me loud and clearly as well. I'll intentionally again slow down my pace as well, so we can all hear loud and clear as well. So we have the low income and high income earners, and we formed our clusters. And we were talking about the fact that when we said for the KNN, we used the K to determine how many of the neighbors we were circling around the unknown data, right? So we had, in this case, in our case, we had the Huskies against the Hounds, and then we said we were going for K of 5, so we selected 5 neighbors. That the K determined what kind of neighbor, how many neighbors we're putting in the circle. The same way for k-means, which is an unsupervised machine learning algorithm, we use the K to specify how many clusters the model should try to create. Yeah, so K, in this particular case, what is the number of K? What is the value of K that we are using in this case? 3. That's perfect. So right on spot. So we can actually then say, okay, we have these 3 classes. Either you belong to the alpha class, which is low income, high earning, or you belong to the theta class, which is low income, low earning, or probably the beta class. And based on the strategy, we can say maybe we're targeting the beta class, or we're targeting the alpha class or the theta class. Then we can actually plug into the data to help us categorize or label the data and form our classes. So the whole strategy is just to find like for like, right? High intra-class similarities, right? And then we want to put them in the same group. And then the ones that are not similar, we just want as low inter-class similarity as possible. So that is forming this classification or class trains. And we're saying what are some of the possible outcomes we can actually have, which is basically the type of clusters that we may end up with, right? One type that we may end up with is the hierarchical, where you have a particular data point that belongs within a cluster that is also falls within another cluster, similar to, just bear with me, this come up, let me get rid of that. Similar to the way that we may have like nested loops, right? So you have one cluster falling within another cluster that may also fall within another cluster. So you have a data that belongs, or data point that belongs to more than one, or a particular item that belongs to more than one. So you've got boundaries within boundaries, right? Then you can have the partitioning. Partitioning simply means that you belong to only one cluster. So if you belong to yellow, that's all you belong. You can be yellow and red at the same time, or yellow, red, and blue at the same time. So with partitions, it's separate clusters that we have formed and exist in there. Then we can have overlapping. So overlapping where you have one data which falls within several clusters, but not necessarily one cluster simply falling within others, or clusters within others, like the hierarchical. So you have the data point boundaries overlapping each other. So you've got one boundary on top of the other, for example. Then you have fuzzy. So fuzzy in this sense, the question is, how do we tell whether the data point belongs to this cluster or maybe belongs to the other cluster? So with fuzzy, we're using probabilities. And again, probabilities, we start from, we have the range between 0 and 1 in this instance. So we say we're using probabilities. So in this case, we have, let's say, 40% chance that it belongs to red. And again, there's a 40% chance that that data point belongs to the blue, or maybe only, well, lesser percent chance. So there's sort of a split between the chances of this data point either belonging to a red or blue. If we look at another data point, we say, okay, we've got 60% chance or level of confidence that it actually belongs to the red. So it's a bit fuzzy. So think of it as blurry point in between there. Similarly, you can categorize or have a cluster that is mainly based on density, which is how dense an area is in terms of the data point that is falling within them. That kind of give us an idea of the possible classes that we can have, right, in terms of the classification. And we're saying that one of the popular or unsupervised machine learning algorithms is the k-means. So we want to have a look at the k-means into a bit more details, right? It's unsupervised, it's learning from the data that is given to it in terms of looking at patterns, and it's going to try to classify them based on the k that we specify as well. So it's going to try to create some things like this for us. Okay, so really quick intro into how the k-means work. Can I just pause to see whether you can hear me clearly? There are no questions. You're okay for me to continue? Okay. So here we say k-means is a type of partitional-based clustering. So basically it means that each data point belongs to one and only one cluster. That is how the output is going to look like. You're not going to have overlapping points. So in this case, we've got a k of 3. We'll try to group the data in this particular order. And I mean, that's the best it could do, but there are not going to be any overlap. So it's just a partitional-based clustering approach. So if we take, let's say, 12 data points, this is our original data. We've got 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. My counting skips. So we've got 5, we've got, say, 7, 8, 9, 10, 11, 12. Yes, we've got 12 data points, and then we want to cluster them, right? So this is how the k-means algorithm works. If we specify the k, so we take an example, we specify the k to be 3. It will try to randomly place some centroid. Let's call it center of gravity. I'm just making that word up because it kind of gives a clearer illustration for it. So it places, it's a centroid actually, but if it places the center of gravity there, so at this point, what it's going to do is to try to pull this close to it, in that sense that all the nearest data to it will be circled to be put in the same cluster, right? The approach that is used to find the clusters in terms of how the k-means work is called expectation maximization. So we'll split it to the expectation phase and the maximization phase as well. Hopefully you can see, and that's a Z and that's a TION. Yeah. So we have expectation maximization. Now it has to find a way, to place these centroids on the among the data points. So try to find a way to do that. And the way to do that in the first instance is by random distribution. So we've specified a k of 3. So it will place 3 of these centroids randomly on the data. So just place, sorry about the stacking thing overlapping there. So just place the centroids randomly among the data points. It doesn't necessarily have to be at a point which our ground truth data is already occupying or the original data is occupying. It's just randomly distributes them. So our K of 3 have this, and it's going to try to calculate the distance closest to of each data point and try to find out which ones are closest to our centroid that has been placed there. And the way it does that is the Euclidean distance that we calculated earlier, which is basically take the X of the data point, take the X of the centroid, and then take the Y of the data point and the Y of the centroid. Try to find the difference and then square them, and then of course add, and you find the square root. So because you don't want to be dealing with complex numbers in that particular case. So it's just how far it is from the centroid in the cardinal point. It's got an example here. So you've got 3, 3, and then 4, 2, and you can actually just, of course, subtract, plug it into the calculation to get something like 1.14. And you do it for each of them, find the smallest distance and try to group them. So in this particular case, we do it for each of them. We notice maybe this one was closest. Again, it's frozen, so bear with me. These data points was closest to C2, for example, so they will be grouped into C2, and then we have other data points that were grouped to C1, and we have this C3. So we're done with the expectation phase. We've done some random distribution of the centroids based on the number of Ks that we have. We set our expectations sort of. Now we want to actually maximize the chances of a particular data point belonging to a particular cluster, right? And how we do it, it will be to also to find the average of these. How far they are from the actual centroid that we're looking at. So we place the centroid within this data point randomly, place it in there, find the average, place it in there, find the average. So we keep adjusting that until, of course, we have actually maximized the chances of them being closest to a particular centroid. Yeah, so we just randomly keep placing the centroid, which looks like the center of gravity in there. You notice that the more we do that, the higher the chances of maybe a particular data point falling outside one cluster to fall within another cluster. So we're just going to keep placing them and then finding the average at that point. So just move it around a little bit. So move it around within the cluster, move it around within the cluster. We're likely to lose a data point to the others. And each of them, we will just keep calculating the average at that point where we say, take each of the data points, including the central point, and then have the average of that particular point. So just we'll calculate a cluster central for us. So once we keep doing that, we notice that we will eventually come to a point of convergence, right? We get to a point where the centroid is not really changing anymore. So we have some data falling outside. Eventually, we've lost some data that originally belonged to the red. We've lost actually most of them to probably the blue and some maybe to the yellow. And we come to a point of convergence and we say, of course, we're not seeing much changes. Our clustering is done. And that is how it's learning from the patterns to create our clustering for us. Now, these are the points that we note, right? This is unsupervised learning. You've not labeled the data. It's just simply learning from the data to do the classification for you. Then we also selected RK. So we don't really know whether this is really the best method. We still have a bit of decision to make, which is what is the best K to use based on the data? What is the K location and other things? So there is a bit of extra things that we need to do in terms of our decision making, and there are different techniques that can be used to determine what is the best K. But I'm happy to stop at a point where we've just simply understood how the K-means algorithm work. And I'll stop the recording here on the presentation and give you the chance to ask questions if you have questions for me. Are there any questions for me? Or have I lost everybody? Okay, we're on mute.
No questions.
No.
Can I confirm with you? I know we are close to the end and of course energy is dropping, but can I confirm with you, do we roughly understand how the KNN works?
Yes.
Do we roughly understand how K-means work?
Some people say no.
Okay, so those saying no, can you please give me the chance to at least look at where I lost you so we can probably do some reverse and do a quick chat about it.
Could you please go over the centroid part?
Okay. So basically, I've stopped the recording, but let's hope I'm just going to go through each of the slides. I don't know, I should get rid of that thing on there, right? So basically, this is the data that we have, similar to what we've done in the past. We've got our original data set, place it in the Cartesian place. We're thinking we probably have feature B, feature A that we're looking at, right? And we've set our K to be 3. We are okay with that, which means we're going to find evenly distribute some centroids, C1, C2, C3 evenly, randomly, sorry. Just place them randomly within the Cartesian plane. It doesn't have to be overlapping on any of these. It's just really random at this particular point in time. Are we okay with that? Okay, up to this point, yes?
Yes.
So based on how far, we just simply see which data point is closest to which centroid. So if these ones were closest to that, we'll just draw that. And the way that we determine whether it's closest to that, it's quite similar to our answer we gave to when we did the KNN, how we found the closest neighbor, right? It's just simply its position in the Cartesian plane, and then we just subtract them. So we find that of the data point, and then that of the centroid, and then the same, we do the same for the Y, and we do the same, well, sorry, for that of the data point and that of the centroid as well. Then we just simply subtract them, and we're going to add them in the first instance, just mathematics, but as long as you understand, we have the person, right? So we all okay up to this point. Try to find whichever data point is closest to which centroid. That's why I'm saying view of it as a center of gravity, like gravity pulling it in. We all okay up to this point?
Yes.
Okay, so based on that, once it's calculated, whichever is closest and everything, mass come in, we jump up and we come up, do our calculation. It would then it would say, sorry. Can I continue?
Yes.
Okay. So based on that, we can actually say in our first instance, based on the randomly distributed centroids that we had, this.
Michael,
Yes, hello.
I think we're out of time.
Yes, we are. If I'm happy to stop here, those who have to go can go. I can just briefly explain it to the one person who asked the question.
Yes, okay. So I think that was Chuda, right? Yes, Chuda. Chuda, you have a question.
If
So you can reach out to him privately. So you can reach out to Michael privately if you have any questions. Alternatively, you can also come to Kweku today for office hours. You'll be available till 8 p.m. today, right? So yes.
Yes.
Yes. So I announced at the start of the class that even though, so the lab was initially canceled because of the talk, but the talk has been canceled now. So we're going to have the lab.
Okay, you guys should send Michael and Dr. Costa emails.
Please don't do that. They beg you. Okay. Mike, do you have anything else you want to add on?
Yeah,
Okay, I think there's a question in the class.
yeah. If just wrapping up the other question, simply after the first centroid is placed and you've calculated the minimum distance, that's what we're doing at the moment. Oh, please, if you need to go, I'm happy for you to go, but please leave quietly for the benefit of those who want to stay. Um, So basically, all you do at this point is to keep varying the position of the centroid. And each time you vary it, you want to find, so we are thinking of maximization at this point, right? And with the maximization, you take the centroid or you take all the data points and you are trying to find the average. Let me bring it back up for you. So you're trying to find the average. So you take that XY of the data that you have and everything, and you just simply finding it with the new centroid that you've picked up and you're finding the average of it. So each of them, one that gives you the best average will eventually fall as the right centroid to use for that cluster. And all I mentioned was that whilst you do that, you likely lose a data point to the others to come up with a new different cluster. That's the only point I've sort of touched on.
Hello, Michael.
Hello.
Yeah. Hello, Michael.
Yep.
Thank you.
Please. Please, we just found out that the meeting has been cancelled, so we wanted to find out if class could be online tomorrow.
You have another class.
Sorry, that's not a question for me to answer because I would adhere to your university's policy. So that's something that has to be discussed with the team, and Dr. Kosa will let you know. But I believe that we're having it anyway. So Dr. Kosa will let you know whether there's a potential of it being online. I don't think it's a decision for me to make.